Hello everyone, limits and differential calculus day number 9. Topics for today are approximations using the derivative, using the local linearization method, as well as the mean value theorem. Let's get started. Alright, so let's talk about this idea of differentials. So dy and dx are called differentials. Dx represents the change in x of both the tangent line and the function, and dy represents the change in y along the tangent line only. Now that may or may not make sense to you yet, but what I'm going to do is I'm going to do a little work here graphically and see if I can explain this. Okay, so as I look at this graph, let's call this value x equals a. Let's call this value x equals b. That would make this approximately equal to f of a, and this approximately equal to the output there be f of b. Now this length here I'm going to refer to as delta y, right? That's the change in y, right? Or the change in f of x with respect to y. Okay, now same thing here. I'm going to refer to this length here as delta x, which is just the change in x, or b minus a. So delta y is f of b minus f of a, and delta x is b minus a. All right, so now let's think of how we can isolate and determine how dy and dx relate to this situation. Okay, so we refer to dy and dx typically in the form of a derivative, right? So the slope is the derivative, and therefore the slope or the derivative at a, if I were to sketch that, right, the slope from this point here to this point here would be change in y over change in x. That's where the dy and the dx come into play. Now let's relate delta y and dy. Here's delta y. Notice that dy and delta y are not the same value, right? So dy is an approximation of delta y. Now, how could I make that approximation better? Well, I could shrink delta x. So I could shrink delta x closer and closer to 0. That would make it a better approximation. Okay, let's dig in a little bit further. So we know that delta y is equal to f of b minus f of a. Therefore, f of b is equal to delta y plus f of a. Well, since I know that delta y is approximately the same as dy, I could say that an approximate for f of b, or an approximation, would be f of a plus dy. Now, how do we find dy? Using derivatives. Well, let's look at the next step here. The slope of the tangent line given in terms of dy and dx, we said was, dy over dx. Now, we typically refer to, when we talk about f of x, that the slope of the tangent line is f prime of x. So if I manipulate to find dy, dy is actually equal to f prime at x times dx. And so therein, we can estimate the change in a function, right? This is the change in the output of a function in terms of delta y and delta x. Okay, so let's go on and use this in the next slide here and show you the application of said item. Okay, first things first, let's get a little practice finding dy, and then we'll use that differential to find some approximations. So example 1 says y equals x squared. Write the derivative in differential form and then find dy. Okay, so differential form for the derivative would be that dy dx equals 2x. Right, this right here is f prime of x. Now I'm going to multiply both sides by dx, so I'd get 2x times dx. So I've got f prime of x times dx. There's dy. That's how we approximate the change in y by using the derivative. Okay, let's do the same thing in example 2 and then use it to apply it to approximations. So find the differential dy. So dy dx, the derivative of square root of x is 1 over 2 root x. Therefore, dy is equal to 1 over 2 root x times dx. All right, again, change in x, and this is f prime of x. All right, let's evaluate dy, and then delta y. Recall that delta y is equal to f of b minus f of a. Now, in this case, a is going to equal 1, right, because that's where we're evaluating, and b is actually going to equal 2. And the reason I know that is because delta x equals 1. So if a equals 1, then b equals 1 plus delta x. All right, that's the change or the length of that interval. Okay, so let's find dy. We already know the equation for dy. dy is equal to 1 over 2 root x times dx. Well, dx is 1, and a, right, is also 1. So dy, the approximation for the change of the square root function, is 1/2. Let's find delta y. Delta y is the actual change in the square root function, and we'll see that visually in part C here. So f of b, so that's the square root of 2, minus f of a, that's the square root of 1. So the actual change, delta y, with a calculator, I believe that comes out to be 0.414. So you can see how I estimated a change of 1/2, but the actual change was 0.414. Let's see that happen on a graph here. Okay, here is the square root of x. Here is x equals 1, so the output for x equals 1 is 1. The output for x equals 2 is the square root of 2. Okay, so here you can see is actual delta y, which we said was 0.414. However, okay, let's sketch this out real quick. Here's delta x, which is equal to dx. Here is delta y. But using the tangent line equation, we get this small error here, right? Because this right here is dy. We said it was 1/2, so this would be 1 and 1/2. Okay, you can see that there's a slight error. That slight error takes place here, which we could find by subtracting dy and delta y. Okay, but you can see how the tangent line approximates our output, but isn't exact unless the function is linear. Okay, so let's look at part D. It says approximate the square root of 1.1 using differentials. So I want to find the square root of 1.1. Well, that should equal the square root of 1 plus delta y, right? So think about that logically. Let's sketch it out. Oh, that was bad. Let's try that again. You may not have seen that. Here's x equals 1. Here's x equals 1.1. Okay, so here's square root of 1.1. Here's square root of 1. I'm going to approximate it. So in order to approximate it, I sketch the tangent line. So this would be an approximate value for the square root of 1.1 right there. It's going to be an overestimate, and that's totally fine. So let's use dy, right? Because we don't know, we're not going to like cheat and use the calculator. But dy, we're going to sub in for delta y, and therefore it will not be equal, it will be an approximation. So the square root of 1.1 will approximately be equal to 1 plus dy. Well, we said that dy is equal to 1 over 2 root x times dx. In this case, dx is equal to 1.1 minus 1. So dx is equal to 0.1. X is still equal to 1, right? That's where we're projecting our tangent line from. So dy is equal to 1 over 2 times the square root of 1 times 0.1. Okay, so using that, that would be, let's see, 1/2, which is 0.5, times 0.1 comes out to be 0.05. So I'm approximating that the square root of 1.1 is equal to 1.05. Okay, now what I end up getting using the calculator is that the square root of 1.1 is equal to, and I'm going to round to, let's go 4 decimal places, 1.048. Those are pretty darn close. Now I can say equal to, right, because I used my calculator here. But notice that this is an underestimate, right? My estimate here using differentials is an underestimate. Excuse me, an overestimate, right? And the reason why it's an overestimate is actually because the function is concave down. So the slope will project above the function if the function is concave down. All right, let's look at some more here and move on. Okay, so example 3. The radius of a circular disc is given to be 24 centimeters. So I'm going to say r equals 24 centimeters with a max error in measurement of 0.2 centimeters. So that's going to be our change in r, okay, or dr. Use the differential method to estimate the maximum error in the calculated area of the disk. Okay, so area with respect to r of any circle is pi r squared. So the change in the area with respect to the radius would be 2 pi r. I just took the derivative of pi r squared. So the change in the area, right, or the estimated change will be 2 pi r times dr. Okay, so our approximate change in area would be 2 pi times the radius, which is 24, times dr, which is 0.2. Okay, so what is this really giving us? This is giving us an estimate for the change in the area given this small change in the radius, which comes out to be, I believe, what is that? 48 times 0.2, which is 9.6 pi. And that would be centimeters squared. Let's see this take place graphically. All right, here is the function pi r squared, which is our area function in terms of r. Here's 24, and let's go out here to 24.2. So you could see that dr, which is delta r, is said thing. Okay, if I were to project, here would be dA. All right, I'm not looking for delta A. It's not asking me to find the actual value, but I want dA. Okay, that ends up being equal to A prime of r times dr. Okay, just like dy ended up being equal to f prime at x times dx. Okay, and A prime at r ended up being 48 pi, and dr was 0.2, which gives me an estimate for the maximum possible error, which would be 9.6 pi centimeters squared. All right, there you go, guys. That's a little bit on differentials. Now let's get into some local linearization. All right, so local linearization is very, very closely tied to the idea of differentials. Okay, let's come up with a formula now for finding the local linearization, or an estimate close to a point using the derivative. All right, so consider the function f of x at the point x equals a, write the equation of the tangent line. So it's kind of slowly walking us through this. But what is the ordered pair at x equals a? Well, at x equals a, we get a comma f of a. All right, so I've got a point a f of a. Now I need a slope. Well, the slope at that point would be f prime at a. Therefore, the tangent line equation would be, using point slope form, would be y minus f of a would be equal to slope f prime at a times x minus a. All right, now we're going to add this f of a over and leave the f prime of a minus x minus a. And then we're going to actually use this to approximate. We're going to call this the linearization function, L of x, f of a plus f prime at a, x minus a. This helps us to get an estimate along the slope of the line, or along that tangent line, for f at some other value, x, right? So I want to bring this back to what we did on the previous slide. We said that f of b was f of a plus dy, where it was approximately equal to that, right? Well, this is dy because it is f prime at x times dx, right? This is your change in x. This is your slope at said value, and there's f of a. So this is very closely tied to what we just did on the previous slide. Let's go ahead and use it on the next slide here. All right, example 1. Determine the linearization equation for f of x equals square root of x at x equals 100. Then draw it. I'm actually going to draw it first. Okay, here's the square root function. Here's x equals 100. The square root of 100 is 10. Therefore, I'm going to write an equation for this line right here. All right, so I need two things. I need a point and I need a slope. So the point here is 110. And the slope on that, well, I'd have to use f prime of x, which is 1 over 2 root x. So f prime at 100 is going to be 1/20th. Therefore, I could write the tangent line equation, y minus 100 is equal to, y minus 10 is equal to the slope, which is 1/20th, x minus 100. Okay, and then when I add 10, I'm given now my linearization model. That'll be 10 plus 1/20th, x minus 100. So if I want to approximate the output for, let's say, the square root of 100, right? So the square root of 101 should be approximately equal to L of 101. Right? So where would L of 101 be? Oops, 101. Well, it'd be right here. It'd be a little bit bigger, right? Just a tiny bit bigger than the actual output of the square root of 101. And we can tell that that output will be an overestimate for the actual function value. So let's do it. Let's finish it up here. Let's find L of 101. That would be equal to 10 plus 1/20th of 101 minus 100, which is 1. So L of 101, our tangent line approximation using this linearization method, would be 10.05. Okay, when I use my calculator, the square root of 101 comes out to be 10 point, oh boy, I lost it. Where'd it go? Calculator. Oh, there you are. Okay, 10.049 and some change. So you can see how dang close that is. This was my approximation, right? And this is my actual. All right, let's do the same thing for square root of 99. Square root of 99 should be approximately equal to the linearization approximation of 99. linearization of 99 ends up being 10 plus 1 over 20 times 99 minus 100, which is negative 1. So L of 99 comes out to be 9.95. Okay, that's my approximation. My actual, using the calculator, comes out to be 9.49. 9.949, so darn close, right? Again. Therefore, again, right, we said that the function is concave down. How do I know the function is concave down other than just looking at it? Well, if I were to take the derivative of said thing, I would get negative 1 over 4x to the negative, or excuse me, x to the 3/2. You could take that second derivative yourself, but it doesn't matter what value I plug in for x. F double prime of x is always less than 0, which means it's concave down, which means the linearization method will always give me an overestimate. Okay, it says use your calculator to see how accurate your estimates were. I actually did that. Pretty close, right? You can see how close those are. Let's go ahead and keep on moving. All right, so here's an example. Slightly different flavor, same topic. We're going to use our linearization method in order to find an approximation for a 0 of f of x. So what is a 0 of f of x? That's a value such that the output equals 0. So I want to know an approximate now for x. Okay, prior to this, we were finding approximates for y, or the output. So let's use what we know here. I've got a 0.35, and I've got a slope at 3, which is equal to negative 2. So I can write my approximation linearization equation. I'm going to take L of x. Remember, we're going to take f of a plus f prime at a, x minus a. So what is a here? Well, a is 3. So L of x will equal 3 plus f prime at 3, which is negative 2, x minus 3. And I made a mistake there. My bad. That should be f of a, not just a. So f of a is 5. All right, so if I want to know an approximation such that the function has a 0, I want L of x to equal 0. Now again, this will be approximation. This isn't going to be exact. All right, so let's see what we get. I'm going to subtract 5 and divide by negative 2. So I'll get negative 5 over negative 2, which is just 5 over 2, should be equal to x minus 3. Well, 3 is really 6 over 2, so I'm going to add 6 over 2. So it looks like my approximate value for the 0, so f of 11/2 should be approximately equal to 0 according to my linearization model. All right, outstanding. Let's move on to the last topic for today, which is the mean value theorem. All right, so the mean value theorem. If f is a differentiable function on a closed interval a to b, then there exists a number c between a and b such that the derivative at c, or the slope of the function at c, should equal f of b minus f of a over b minus a. This is just the slope of the secant line from a to b. Or equivalently, f of b minus f of a should equal f prime at c times b minus a. So what is this? This is really dy, and this is f prime at c times dx. Okay, all of these are really closely tied in together. Let's look at what that means geometrically. So the mean value theorem, let's say I have a function, looks like this, and I go from a out to b. What would the slope of the secant line look like? Well, the slope of the secant line would be f of b minus f of a over b minus a. And the slope, or the secant line, would look like that. What is the mean value theorem saying? It's saying that the slope of the tangent line at some value c has to be equal to the slope of the secant line. So the slope at some point, at least one point, okay, has to equal that. Well, I would say that maybe about here and possibly about here. I've found two C values such that the slope of the tangent line looks to be parallel to the slope of the secant line. That's what this means geometrically. All right, so let's look at an example here in a second, but first reiterate that the function must be differentiable in order for the mean value theorem to apply on the entire interval. So it's got to be differentiable from A to B in order for this to work. Let's look at an example of that in the next slide. All right, it says find the value or values of C such that they satisfy the mean value theorem for f of x equals x plus 1 cubed on the interval from -1 to 1. Okay, so let's review what the mean value theorem says. It says that the derivative at a point C needs to be equal to the slope of the secant line on the interval at least one point, possibly more. Okay, so first as I dissect this, I think, well, I got to find the derivative. Well, the derivative of the function, if I use the chain rule, will be 3 times x plus 1 squared times the derivative of x plus 1, which is x plus, or 1, excuse me. So f prime at C will be 3 times c plus 1 squared. Okay, I'm going to plug that in. 3 times c plus 1 squared. Now f of b minus f of a over b minus a is going to be f of 1 minus f of -1 over 1 minus -1. Well, f of 1, if I plug that in, I get 2 cubed, which is 8. F of -1, if I plug that in, that's 0 cubed, which is 0. 1 minus a -1 is 2, so that should equal 4. Now I'm looking for at least one value of C such that this equation would be balanced. Okay, I'm going to divide by 3 and take the square root. That'll be plus or minus. If I take the square root of 4, I get 2. Take the square root of 3, I get square root of 3. So it looks like C will equal -1 plus or minus 2 over the square root of 3. So C equals -1 plus 2 over root 3, and C equals -1 minus 2 over root 3. That tells me that f prime at -1 plus 2 over root 3 is equal to f prime at -1 minus 2 over root 3, which is equal to 4. All right, outstanding. That's it on mean value theorem, local linearization, and approximations. See you in the next video.